All right, so for the chapter 16 to 17 of the simple linear regression, we have one more part to cover, which is the last step of the simple linear regression, which is they validate the model, right? So we say, based on, in our example, we say, based on the 52 stores, we got the simple linear regression equation, which is 2775 minus 248.9x, right? It is based on the 52 stores. In this 52 stores from a random sample, in this sample we call it is training sample, right? So the training sample is the one we use to generate the model. All right, and then we need another sample to validate the model. So this sample we will call it is the validation sample. We want to validate this equation, whether this equation is good for the population model or not, right? So we need to make sure whether these 52 stores are representative for the population, or for some chance this sample is an extreme case, right? So we need to validate the model we had based on this training sample. All right, so here, this is the output. Remember, this is the scatter plot of the 52 stores, and then based on these 52 stores, we have this equation, right? Linear regression equation. We have the three tables. And then to validate the model, we need to use another sample to calculate, we call it is the validation MSE. Remember that in the last video, we said to decide whether the model is a good model or not, we need to calculate the MSE, although it is from the output, but we also need the value of MSE. We want the MSE to be as small as possible, right? So that means for the training sample, we have already got the MSE. So this is the MSE for the training sample. And now I have another sample, which is the validation sample. And then we want to calculate its validation MSE. All right, so now let's see how to calculate this validation MSE. So for this process, I will not ask you to calculate this validation MSE. I just want to show you how to get this validation MSE in your future research or the projects. All right. So first, you need to make sure that your validation sample, right? So this validation sample should not contain any observation in the training sample. So you need to choose another sample that do not contain any observations in the training sample. This is a new sample. All right, so this validation sample should not be included in the training data. So here I just used I just use 5 of them, for example. But actually, if the training sample is 52 of them, then the validation sample should be at least half of it, which is 26 observations. All right, so to make the note as short as possible, I just use 5 of them. So suppose my validation sample contains 5 observations. Then how you can calculate the validation MSE. So remember the MSE is based on the residual, right? So we calculate the residual for every observation and then square it, sum of all the residuals, square the residuals together, and then divide by how many of them. Divide by the degree of freedom, n minus 2. All right, so now let's just use this Excel, this table to show how to get it. Right, so first, what is the price? This price is X, right? Okay, what is the Y? Y is the cases sold, right? So this column is for the Y. And then based on the X and Y, we get the linear regression equation, right? So that we can calculate the Y hat based on this linear regression. That means for every X, you can calculate the corresponding Y hat, right? So this 226.264, that means will be 2775 minus 248.9 times the corresponding X, which is 10.24, and then you should have the Y hat, which is 226.264. All right, so that means this column is just based on the regression to get the predicted value of Y. And then our goal is to find the residual, right? So remember, what is the residual? We say the residual will equals to Y minus Y hat, right? So which is the observed Y minus the predicted Y, right? So what is the residual here? The residual is the Y minus Y hat, the 220 minus 226.264. So you have the residual for this observation, and then you need to do the same thing for the rest of the 4 observations. All right, so I got the residuals, and then next step is to get is squared, right? So I have E squared, which is the residual square for every observations. And then, all right, so we have the E squared, the residual square for the summation from the first observation to the nth observation, right? So that means I need to sum of all these residual squares together, right? So it will be 39.24 plus that, plus next one, plus this one, plus this one. That means I will get sum of it, which is 166,043.5. All right, and then this is the top of the MSE. Divide by n minus 2. Now it will be divided by 50 or 3. This n right now will be the sample size of validation sample. All right, so this is the sample size of validation sample, which we have 5 of them, right? Then it will be 5 minus 2, which is 3. So you have that divided by 3, and this is your validation MSE. All right, and then if you take the square root of it, then we will get the validation standard deviation of the residual, which is just the square root of the validation MSE. So you will get the 235.26, which is, we call it is validation standard deviation of the residuals. All right, so until now we get all the information we needed for the simple linear regression. But until now, you may not have any idea about, okay, for a model, I know that I want the R squared to be as large as possible. I want the MSE to be as small as possible. But how small it should be, say, small, right? How small is small? How big is big, right? So we say when R squared is close to 1, that means it is big. But MSE, you don't know whether it is large or not. So why we want this MSE or validation MSE? We want to compare models. All right, so now let's think about any other options or any other linear regression models can describe this data set. All right, so since in our old regression equation, which is this one, right? When we check the assumptions, do you remember? When we check the assumption, we have two assumptions not satisfied, right? Which is the equivariance assumption and normality assumption, right? So these two were not good for our old regression model, right? Regression equation. So we want to try something else, right? So the most common way to try something else we call to make a natural log transformation, right? So transformation. Normally we do the transformation about y, but sometimes it also can do with x. So most of the time we do the transformation about y. So how we can do the transformation about y? We say, okay, so when we look at this scatter plot, right? So it looks like linear, but it is not strong linear, right? And then not this one, this one, yeah. So this is shows some linear, but actually if you look at the details, it looks like more curved, right? You see that? It's like more like curved relationship, right? So although you can consider it is a linear relationship, but it is more like a curved relationship, right? So then for this case, if you see a kind of curved relationship, then you can do the natural log transformation about y. So how you can do the natural log transformation? That means so how we can make the natural log of y, how we can make the regression based on the x price with the natural log of y. So it will be easy. So now let's go to our data, right? And then we say the price is x, the sale is the y, right? And then now we want to create another column. And for this column, I can right click and then you can customize the column information. So first I say it is this column is for the natural log of the response variable, which is cell, natural log y, right? And then let's say we want a formula. We want to calculate this natural log of cell, right? So we need to create this formula, which is the natural log of the cell, right? So if you enter that, right, and then apply, and then click OK, you will have one more column. So what is this column? This column is the natural log of the cell for each observation. And then we can do the regression for the x, with natural log of y. Alright, so now we can do the analyze, fit y by x. Now the x will be still the price, but now my y, my response variable, is not the cell anymore. It will be the natural log transformation of the y. Alright, I want to do the regression based on these two variables. Alright, and then click OK. Alright, so now if you look at the scatter plot like this, right, it will not be like curved as before. It is more kind of more linear, right? Okay, and then we can check the assumptions. So we have the scatter plot. We want to also see, I want to fit the line. Alright, and then based on the line, you see the natural log of cell will equals to the b0 minus b1 times x. Alright, so now your response variable will be the natural log of cell. Alright, okay, now if I check the residual, so where is the plot residuals? Right, so we don't need this, we don't need this, we don't need that. Alright, so we have this residual plot. Remember what we had before? In the last class, the residual plot for the original one is like this, right? So we have the fan shape. That's why the equivariance assumption is not checked. But now if you look at this residual plot, the points are equally spread out, right? So it is equally spread out about this 0 line. Alright, so that means the residual plot is okay. Alright, and then for the histogram of the residual, it doesn't look like the normal shape, right? But if you look at the normal contour plot, they kind of follow this line, which is much better than the one we had before. You see that? Right? So it is curved, but now most of the points follow this line. Right? Okay, so that means after we do the transformation and then make the regression based on the natural log of y with x, then the assumptions getting better, right? So that means for these two cases, we can say this one is good, this one is also kind of good, right? Okay, that means it looks like, based on the assumption, it looks like this regression equation is better than our original one, which is 2775 minus 248.9x. Alright, okay, but the point is how we can interpret this b0, how we can interpret this b1. These three tables, this linear regression is based on the x is price, the y is natural log of y hat. Alright, so that means now your y variable changed. Of course, your b0 and b1 will be changed. And then you will have this new linear regression equation based on the x and natural log of y hat. But the problem is now how you can interpret this b0, how you can interpret this b1. For b0, it may be easy because it's just that when x equals to 0, then the natural log of y hat will equals to 10.17. That means, but we cannot just say this, right? Because we want to know something about the y hat, about the cell. We cannot leave it natural log of it. So what is y hat? Y hat will be e to the 10.17, right? But what about b1? b1 is a slope. We say when x increase by 1 unit, the natural log of y hat will increase by the slope, which is, for this case, will be decrease, right? Will be decreased by 0.46. All right, so can we just say then the y hat will decrease by e to the 0.46? Actually, it is not the case, because when x equals to a, let's do the practice again, right? So we have natural log of y hat will equals to 10.17 minus 0.46x, 0.1646a, right? But we want to know about y, so y hat will equal to e to the 10.17 minus 0.46a, and then we can write it as e to the 10.17 divided by e to the 0.46a. Alright, so this is the result for when x equals to a. Alright, then let's say when x equals to a plus 1 increase by 1 unit, then we have the natural log of y hat will equals to 10.17 minus 0.46 times a plus 1, which is 10.17 minus 0.46a, and then minus 0.46, right? And then we have the corresponding y hat will equals to e to the 10.17 minus 0.46a minus 0.46, which is e to the 10.17 minus, not this minus 0.46a divided by e to the 0.46. Alright, so let's erase that because we don't need this step. Alright, so what is the top here? What is the top here? The top here is just a y hat when x equals to a, right? So that means when x increase from a to a plus 1, the y hat kind of decreasing by this rate. Alright, so that means when we make the transformation, although we have better assumptions checked, but our linear regression is much harder to explain the coefficients, right? It's much harder to explain what does this b0 mean, what does this b1 mean. And then we'll also want to do the same thing. We want to validate our, now this is our new regression, but here this y hat is not just the cells, right? This y hat is actually our natural log of cells, right? So this is our new sample linear equation based on the price and natural log of cells, right? Okay, so based on this regression, we can still choose the same validation sample and to see whether this example is good for the validation, right? So we'll do the same thing, so that we have the price as x, right? And then our original y, which is the cell, is this column, all right? And then based on this regression, we plug in the x, which is the price, we will have, actually it is natural log of y hat, right? Okay, and now we want to get the residual here. That means will be the observed y minus the predicted y, but now we have the natural log of y hat. That means we need to do the exponential to get this y hat, right? The real y hat, right? So we need to do the e to the natural log of y hat. So the e to the power of this much for each observation to get the y hat. All right, and then we can get the residual based on these two columns. Y minus y hat will be the residual, so we use 220 minus 239.78, which is this for each observation, and then everything will be the same. You get the residual for this part, for this column, and then you have the squared residual for this column, and then you sum together, you will get it is 229,439.63. All right, and then divide by n minus 2. So since we have 5 observations in our validation example, validation sample, and then we just divide by 5 minus 2, which is 3. And then we have the validation MSE for the natural log transformation regression. Alright, and then if we get the square root, this is the validation standard error, the standard deviation of the residual. Alright, so now we kind of have the two different models for for the same sample, right, from the same sample. So if you write the model for this, it's actually the natural log of y, natural log of mu y will equals to beta 0 plus beta 1 x. In the old one, we have mu of y equals to beta 0 plus beta 1 x. So actually we have two models for the same population. And now we want to compare these two with all the informations you have for each model. Right, and then we just make this table. Right, we say for model 1, we just say the y is cases sold. Right, so this is the original one. And then we have the model 2 is after we did the natural log transformation. Alright, and then the first thing to compare the models, we compare the R square and MSE. Right, so for R square, we had, remember for the old one, we have the R square is 0.737, right? And then for the after the transformation, we have the corresponding R square is 0.7189, right? So in this table, so R square for the first one is about 0.74. For the second model, we have about 0.72. Right, it's not very big difference, right? Okay, now let's compare with the MSE. Remember the MSE is the sum of the residuals, which is y minus y hat squared divided by n minus 2, right? Okay, so the MSE for the model 1 is this big. MSE for model 2 is just this small. Then can you compare these two to say, okay, model 1 is much better than the model 2? No, because what? because this one is based on the cell, but this MSE is based on natural log of cell. So that means the units are different for these two models. So you cannot compare the MSE based on different units. You cannot compare, let's say, 100 centimeters with 1 meter, right? So we don't say the 100 centimeters is higher 1 meter because 100 is larger than 1, because they have different units. So you cannot compare them with different units, right? So that means for this case, we cannot compare MSE because they don't have the same units. Of course, the same thing, we cannot compare the root MSE. But we can compare their assumptions, right? So since the sample is randomly selected, so it will satisfy the independence assumption will satisfy for both cases, right? Then we just check the other three. So for the linearity assumption, it is okay, right? For the model 1, it shows kind of linear relationship, but later we say it's kind of also show a curved relationship, right? And for the linearity for the after you do the transformation, it is also okay. It is still not strong, right? So both of these two are okay. And then for the equivariance assumption, we say equivariance assumption is not okay for model 1, but it is okay for model 2. And for normality assumption, the points didn't follow the straight line in the normal contour plot, so it is not okay. But normality here in the model 2 is okay, right? And then when we calculate the validation root MSE, which is the validation SE, the validation root MSE for model 1 is 235, and then validation root MSE is 276. Remember, when we calculate validation MSE, we already changed our natural log y hat to y hat to calculate the MSE, right? So that means the validation MSE, we have the same unit, right? So if they have the same unit, we can compare them, right? So for this case, that means the validation MSE is smaller than the validation MSE in the model 2. Then what does that mean? We want a better model will with a smaller MSE with a higher R square, right? So for this case, model 1 have larger R square, smaller MSE, but the assumptions are not okay compared with model 2. And then we need to balance the benefit and the bad things. So for this case, if I am the one to decide which model I will use, I will prefer model 1. Because what? Because model 1 is easy to interpret, and it also have larger R square, smaller MSE than the model 2, right? Although they have the good assumptions. All right, but does that mean that if you are the one to decide which model to use, can you just not choose a model 2? If you choose model 2, it will be wrong? No, you can also choose model 2 on your behalf, because everyone make different decision about the linear regression or any kind of regression. Everyone have different ideas. So this is also the undecided part for the regression. There's no single solution for it. So if you do especially in the multiple regression, right? So you will have the project 2, and everyone will have a different model. As long as you think this model is good enough, then you can stop. All right, so there's no, let's say there's no best model based on sample. You can always find a better model, or you can do even not natural log transformation. You can do change y to y square. You can change y to natural log of y square. You can try everything. You can try any transformation, and you can always find a better model than the one you have right now in hand. Right, so even when you make the decision, you can choose the better one you think it is good. Right, but you should have the reason with it. You should at least have the comparison between among all the models you have, and then say, okay, I will prefer model 2 because although for the model 2 it has a little bit smaller r square, a little bit larger MSE, but I will more focus on their assumptions. That's fine. So for this case, if you more focus on the assumptions, then you can choose model 2. All right, so we just use these things to give you a general idea about the simple linear regression, how to choose your linear regression model, and how to make the transformations. All right, okay. And by the end of this model, you should be able to know what's the difference between the population regression model and the sample regression equation, and how to interpret the parameters, how to interpret the statistics, right? So parameters means how you interpret beta 0, beta 1, how you interpret B0, B1, right? And then, yes, so this is not parameters, it will be statistics because it is about the sample, right? And you also need to know how to conduct the hypothesis test, even though the test statistics is given to you, the p-value is given to you, but you still need to know how to state the hypothesis, show the test statistics, and check the assumptions before the test statistics, and compute the confidence intervals for estimating the slope, which is beta 1. All right, and also you need to know how to check the assumptions and how to interpret the r squared, the MSE, right? And if you have a validation sample, how you can get the validation MSE. You don't need to calculate it. You just need to know the idea of the validation MSE. I will not ask you to calculate the validation MSE just like what I did here. Right, I will not ask you to do this table. That's too much work to you. All right, so you don't need to do that. You just need to know, for example, if I gave you this table, can you calculate the MSE, validation MSE, right? So you just sum of the E squared and then divide by n minus 2. All right, and then the last thing is about evaluation of the goodness of the predictive model using the validation sample. Right, so we have already talked about that. We will have the validation MSE. All right, so until now, we are done with the simple linear regression. I totally made 4 videos separately for each part. Right, so the first 2 parts actually is about Tuesday's class, but we have went through the example, so you need to go through this example. And also you are good to complete your in-class practice on the Canvas and also the MyStatLab homework. I will extend the due date of these 2 homework to next Sunday, right? So which is next Sunday will be 22nd. All right, and then you can choose whatever format you want to upload your in-class practice. I showed 3 ways, but if you have any other ways, if you want to write by hand of the questions and then the answers, it doesn't matter, right? As long as you have a file uploaded and then I can grade it, that will be fine. Right, so I know there will be a lot of difficulties, a lot of problems because of this situation. I have too, right? I have a lot of techniques problems, but we can figure it out, right? So just let me know if you have any questions, and if you have any concerns, just be free to email me or make the discussion with me in the discussion session, right? And also, if you have any suggestions about anything, right? So how you can study better, just let me know and see whether we can improve together. All right, so I will make another set of video for the multiple regression, and then if you have time, you can just be free to study ahead of time during the spring break. All right, so see you in the next video.